Hi, so we'll start the 7 tutorial for the Modern Algebra course on NPTEL. The first question for today is consider the ring of real numbers R, that R bar be the ring of all mappings in R. So it's the set of all functions that map from real numbers to real numbers. Let us define the set capital I as the set of all functions in R bar such that these functions map to 0 on inputs 1 and minus 1. Then choose the correct statement. Option A is I an ideal. I is an ideal. Option B says that I is a prime ideal. Option C says that the quotient ring obtained by quotienting R bar with I is an integral domain. And option D says that all statements are correct. So let's go over these options one by one. Let's uh, see option A. So A says that I, the set of all mappings such that they map to 0 on 1 and minus 1, so this should be an ideal. So for that we need to check two properties. First property is consider any f1 and f2 in I. Then let's look at the sum f1 plus f2. We want to show that this sum also belongs to I. So for this f1 plus f2 of 1 should be 0, and this is actually equal to f1 of 1 plus f2 of 1, which is 0 plus 0, which is 0. Similarly, we can show that f1 plus f2 of minus 1 is also 0, which implies that f1 plus f2 is an I. There is another property which says that for all f in I and g in the ring of all mappings, the product f times g should be in I. So for that we need to check the evaluation of f times g on 1, which is f of 1 times g of 1. Since f of 1 is 0, this is equal to 0. Similarly, the evaluation on minus 1 is also 0. So this shows that I is an ideal. So option A is definitely true, but other options could also be true. So let's analyze option B. It says that I is a prime ideal. For a prime ideal, the condition is that whenever for any two functions f and g in the set of all mappings, if the product f times g belongs to I, this should imply that either f belongs to I or g belongs to I. This is the important condition for a prime ideal, right? But is this true in this case? So when we say f times g belongs to I, this means that the product f times z when evaluated on 1 as well as when it's evaluated on minus 1, both of them output 0. This is what it means to say f times z belongs to I. We can further write this as f of 1 times g of 1 is equal to 0, and it's also equal to f of minus 1 times g of minus 1. But note here that it is possible that f of 1 is equal to 0 and g of 1 is not equal to 0, and f of minus 1 is not equal to 0 and g of minus 1 is equal to 0. So when we say the product evaluates to 0 on 1 and minus 1, it's not necessary that any one function will evaluate to 0 on both 1 and minus 1. F could evaluate to 0 on 1 and non-zero on minus 1, but g could evaluate to non-zero on 1 and 0 on minus 1. So then this would imply that uh, neither neither f nor g is an I. So therefore I is not prime. So it's possible that product of two mappings is an I, but neither of those mappings is an I individually. So I is not a prime ideal. So option B is not true. Similarly, option C says that the quotient ring obtained as R bar quotient I is an integral domain. One can use a similar reasoning. So this is do on your own. Similar reasoning as what we did for option B, to show that the quotient ring R bar with I is not an integral domain. So in particular, you can take two different polynomials whose product is in I, but neither of them individually are in I. So option A should be true for this question. If you have any questions, feel free to ask them. Otherwise, I'll move on. Okay, so question 2 says that let F be a finite field containing S elements and with characteristic C. So characteristic is the, so this was discussed in the lecture, the characteristic of a field is the smallest integer n such that when you add 1 to itself n times, you get 0, where 1 is the multiplicative identity of the field and 0 is the additive identity. So let F be a finite field containing S elements and with characteristic C. Let Q be a degree D irreducible polynomial in Fx. Let F prime be the splitting field of Qx. So splitting field was also discussed in the lecture, but I'll just for completeness I'll discuss it here again. So for a splitting, before we go to the notion of a splitting field, the first notion is what's an algebraic extension. So algebraic extension is the quotient field fx quotiented with the ideal generated by qx. So if qx was a degree d polynomial, then this field would contain all polynomials of the form a0 plus a1x till ad minus 1 x to the d minus 1. So these are all less than equal to d minus 1 degree polynomials over fx. So this is called the algebraic extension of the field f with respect to a polynomial q, and this has how many elements? So this will have s to the d elements because there are d terms in the polynomial and each coefficient belongs to the field f. So for each coefficient there are s possibilities, and hence the total number of such polynomials are s to the d. So the size of this is s to the d, and this is called the algebraic extension of a field with respect to a polynomial. And one can repeat this process. So once this we have obtained this as the new field, and here we can take another irreducible polynomial over this field and then repeat this process and keep doing this until, so when we keep doing this until a field is obtained that contains all zeros of the polynomial qx, all roots of the polynomial qx. So we can keep doing this. We keep increasing the size of the field with respect to qx until we reach a point where the field that we end up with, it has all the roots of qx. Then this field, this final field is called the splitting field of the polynomial qx. Right? Now let's go back to the question. The question says that let f prime be the splitting field of qx. Suppose f prime has s prime elements and characteristic c prime. Then how are s prime and c prime related to s and c respectively? So if S prime is the size of the splitting field, we know that this S prime has to be at least the size of this, the initial algebraic extension of F. So it has to be at least this much because whenever we do an algebraic extension, we are increasing the size of the field. So if we were able to get it to S to the D after one algebraic extension, then whatever we do afterwards, it will only increase the size of the field. So S prime should be at least S to the D. Right, the splitting field should have at least s to the d elements. That's there. Then what about the characteristic? So the options only say does the characteristic increase or does it remain the same? But note here that f is a subfield of f prime. So f is contained in f prime no matter what you do. For example, even here when we consider the algebraic extension, all zero coefficients, all constant coefficients, they constitute the field f itself. So f is contained in the algebraic extension, and whatever algebraic extension you're gonna take, f is going to be contained in that. And since f had characteristic c, the final field cannot have characteristic more than c. So c prime is also equal to c. Because since f is contained in f prime, if you take the multiplicative identity of f prime and if you add it to itself c times, you will get 0. And so yeah, the characteristic remains the same, but the size increases, and the size has to be at least s to the d. So option C should be the correct answer for this question. Feel free to ask any questions. Otherwise, we'll move on. Okay. So for question 3, consider the following statements and choose the correct option. Option A says that if f is a field and if an element p is an f, then p can always be written as a finite sum of 1 plus 1 plus 1 till sometimes. So p can always be written as a finite sum. That's option A. Option B says that if f is an algebraically closed field and p is an irreducible polynomial over f, then degree of p must be 1. Okay, so let's look at both options one by one. If f is the field, then any element can always be written as a finite sum of 1 added to itself sometimes. But this is not true clearly because consider the field of real numbers. And if you take any irrational number, it cannot be written as sum of 1. For example, pi cannot be written as 1 plus 1 plus 1 and some number of times. So option A is definitely not true. Right? So let's look at option B. Option B says that if f is an algebraically closed field and okay, so what's an algebraically closed field? It means that for any irreducible polynomial over the field f. So if you consider any irreducible polynomial, let's say q of x over the field f, then the algebraic extension fx quotiented with the ideal of qx. This algebraic extension is contained or is equal to f itself. So if you take the algebraic extension of f with any polynomial, with any irreducible polynomial, you don't get something extra. The field remains the same. That's when it's called algebraically closed. Right? So if f is an algebraically closed field and p is an irreducible polynomial, and let's assume that degree of p is equal to some small d which is strictly bigger than 1. For the sake of contradiction, let's assume this. Then this algebraic extension of f with respect to p, the size of this field is equal to the number of elements in f to the power d. We know this already because this contains all polynomial of degree at most d minus 1. So there are d positions and there are size of f many possibilities for each position. So the size of this algebraic extension should be size of f to the power d. If d was bigger than 1, this is strictly bigger than size of f, which means that the algebraic extension is a superset of f, and this is a contradiction because f is algebraically closed, which means that any polynomial should have degree at most 1. So option B should be true. B is correct, but A is not. In an algebraically closed field, we can't have irreducible polynomials with degree strictly bigger than 1, because then we can consider the algebraic extension and the size of that would be strictly bigger than size of the field. Any questions about this? Okay. So let's discuss the next question. Let C be the field of complex numbers. Let R be the field of real numbers. Let I be the ideal generated by the polynomial x to the 4 plus 1 in Rx. Let F be the field obtained as the quotient ring of Rx with I. Let J be a fourth root of unity, not unity, minus 1 in C. And let F be a function from the field F to C, defined as follows. So if you consider any degree 3 polynomial, ax square plus ax cube plus bx square plus cx plus g, and if you add it to the ideal I, this is mapped to aj cube plus bj square plus cj plus g in C, where a, b, c, d are real numbers. Then choose the correct option. Option A says that f is not a well-defined function. Option B says that f is well-defined, but it's not a homomorphism from F to C. Option C says that F is a homomorphism, but not isomorphism from F to C. And option D says that F is an isomorphism from F to C. So the question says, consider the field of complex numbers denoted as C. R is the field of real numbers. I is the ideal generated by the polynomial x to the 4 plus 1 in Rx. So first note that x to the 4 plus 1 is an irreducible polynomial. Why? Because the roots of this polynomial don't belong in R. So there's no polynomial which divides x to the 4 plus 1 other than itself. So this is an irreducible polynomial over Rx, and hence the ideal generated by it is a prime ideal, is a maximal ideal, and hence the quotient ring Rx with I is a field, and let F be the field given by the quotient ring of Rx with I. Then let J be a fourth root of minus 1. So J to the 4 equals 1. J to the 4 equals minus 1. So it's a complex number. Let F be a function from capital F to capital C defined as follows. So F is only defined on degree 3 polynomials plus I, because these are the elements of Rx quotiented with I. So for any degree 3 polynomial, ax cube plus bx square plus cx plus g when added to I, so this is an element of the domain, and you output aj cube plus bj square plus cj plus g. So basically you evaluate the polynomial on j and you output that. So first point says, is f a well-defined function? The answer to this is yes, because elements of Rx quotiented with the ideal of x to the 4 plus 1 look like degree 3 polynomials. Because any other polynomial you can just take that as a product of x to the 4 plus 1, and whatever remainder remains, that is the that defines the element, and the remainder can only be a degree 3 polynomial. So elements of Rx, elements of this field, they look like degree 3 polynomials, and so f is a well defined function, right? Because it's defined on all inputs, it's defined on the entire domain, so it's a well defined function. Option B says that f is not a homomorphism from capital F to capital C. So let's verify the homomorphic property for f. So first note that for any degree 3 polynomial p of x, the map f when evaluated on p of x plus I, it's defined as p of j, right? So you evaluate the polynomial on the complex numbers j and you output that. So this is how the map f is defined. In order to show homomorphism, we need two properties. So for all px plus I, comma qx plus I, so where p and q are degree 3 polynomials each, what is the sum of what is f of px plus I plus qx plus I? So this is nothing but f of px plus qx plus I. And this is nothing but p of j plus q of j, which is also equal to f of px plus I plus f of qx plus I. Right, so the additive property holds. What about multiplication? So for all px plus I comma qx plus I, what about the multiplication of the two elements? So note that this is nothing but f of the product of p and q, but product of p and q could have degree more than 4, so you have to take modulo x to the 4 plus 1 plus I, because product of P and Q could have degree more than 4, and we need to reduce it to degree 3 polynomial. So you take modulo x to the 4 plus 1, which is nothing but f of px times qx minus x to the 4 plus 1 times some polynomial rx plus I, right? And when this is evaluated on j, this becomes pj times qj minus j to the 4 plus 1 times rj, but j to the 4 plus 1 is 0 because j to the 4 is minus 1. So this is pj times qj, which is also equal to f of px plus I times f of qx plus I. So the multiplicative property also holds, and hence f is a homomorphism. So option B is not true. F is well defined and f is a homomorphism from capital F to capital C. But now we need to check whether f is an isomorphism or not. And to do that, let's check the isomorphism property.